Drifting beyond the last planets are farthest machines, Voyager. Pioneer and new horizons are whispering from the sun's fading edge, where the solar wind slows magnetic fields drape like cloth, and the interstellar medium begins to hum. Tonight we follow their signals through dust lanes, plasma rings, and the thin skin of the heliopause to learn what truly lies outside our star's embrace. If you love calm mysteries and real space discovery, tap like subscribe and ring the bell, then come listen to the universe breathe. He begins at the edge, not with a line, but with a history written in ash and radiation. The sun travels inside a faint interstellar cloud, a lingering breath from ancient stellar explosions that once rippled through this neighborhood. Long before any probe leaves the inner planets, the outer limit of the sun's reach is already shaped by this environment, by thin gas that moves like a slow tide, by magnetic threads stretched across space, and by a soft rain of high-energy particles that arrive from elsewhere in the galaxy. The frontier he will later measure with instruments is born here, where the memory of old fire presses against the outflowing wind of the present star. An interstellar cloud is not dense by earthly sense. It is far thinner than any vacuum made in a laboratory, yet across many light years. Even that whisper is enough to steer charged particles and to drape magnetic lines like cobwebs across a room with no walls. Several nearby stars ended their lives in supernovas, carving cavities and pushing shells that collided, cooled and overlapped. In their wake a patch formed that astronomers now call the local cloud worm, and rarefied, moving gently past the sun. The heliosphere, the bubble blown by the solar wind, grows inside that patch like a lantern's glow within mist. Solar wind begins as a stream of charged particles from the sun's hot outer atmosphere. It expands in all directions, carrying magnetic lines wound into a spiral by the star's rotation. Far from the sun, the wind meets atoms from the cloud that ignore magnetic rules. These neutral atoms drift inward across the border, and later under sunlight or collisions lose electrons and become ions that are picked up by the moving wind. These pickup ions add mass and heat to the flow, changing its pressure and speed. In time, the wind slows, and the place where it first stumbles is called the termination shock. Beyond that lies a sheath of slowed and heated wind, and beyond the sheath a sharper threshold, the heliopause, where the realm of the sun yields to the interstellar medium. None of these names pre-exist in stone. They are outcomes of a balance between the wind that pushes outward and the cloud that presses inward. Move the balance and the drawing changes. Cosmic rays thread through this setting like weather with no clouds, fast fragments of atoms made in distant shocks. The heliosphere deflects many of them, but the shield's strength depends on how firmly the bubble stands against its surroundings. A denser region of the cloud or a stronger magnetic field outside would squeeze the bubble and allow more cosmic rays to seep inward. A thinner region or a gentler field would relax the boundary and lessen the inward drizzle. The sun's own magnetic cycle rides on top of this, swelling and easing the shield over years, yet the larger mood is set by the cloud's long memory. Dust grains carry another part of the origin story. Some dust is local, chipped from comets, and ground by collisions in the Kuiper belt beyond Neptune. Some dust comes from interstellar space, tiny stones that glide on long lines until electric charges and magnetic fields bend them. Far travellers will one day count impacts and find directions. The sun alone cannot explain signs that the frontier is porous and that exchange is constant. Even chemistry at the edge bears the imprint of the cloud. Neutral hydrogen slips into the bubble and trades charge with hot protons in the solar wind. Fast neutrals fly back outward, slow ions remain behind, and the border becomes a zone of swapping, blurring any simple step from inside to outside. The interstellar magnetic field runs like faint wire through the cloud, and where the heliosphere presses outward, that field drapes and folds. Draping matters because it sets the orientation that future magnetometers will read as the craft approach the edge. If the field outside leans one way, the nose of the bubble will compress. If it leans another, the tail will stretch far downwind. No crossing will be exactly the same. In one direction, the field may smooth the way, in another it may form layered folds, a kind of magnetic shoreline with hidden coves. Pulses from faraway stars also shape the frontier. When other suns erupt, their shock waves spread through the galaxy and eventually reach the local cloud. They weaken with distance, yet still carry pressure and a wave of magnetic compression. When such a pulse strikes the heliosphere, it pokes the bubble and sends a disturbance racing along its flanks. Years later, a distant spacecraft may register a brief rise in particle energy, or a ringing in the plasma as that pulse passes. Thus the boundary records events that were born light years away, a drumhead that can be struck from beyond the circle of planets. Over tens of thousands of years, the sun's path wanders through different pockets of the interstellar medium. Some regions are thinner, some denser, some magnetized more strongly, some calmer. The heliosphere responds like a lung that expands and contracts. A denser pocket would pull the edge inward and raise the flux of cosmic rays inside the planetary zone. A thinner pocket would relax the boundary and deepen the shield. Past variations may have swept Earth and its neighbours through slightly different radiation weathers, subtle and slow, but not trivial for atmospheres and surfaces. All of this precedes the moment a probe arrives. Therefore, when planners at the National Aeronautics and Space Administration and partners elsewhere prepare to send recorders outward, they design with this origin in mind. If the border is a living product of a cloud shaped by long-ago supernovas, then one should carry ears for low-frequency plasma waves, eyes for dust compasses for magnetic fields, and counters for cosmic rays. The Jet Propulsion Laboratory builds long-lived craft with power sources that fade with patience, while the Deep Space Network listens with dishes spread across the Earth so that no whisper goes unheard. Each design choice assumes that the edge is not a rigid wall, but a conversation between star and cloud. When the first hints later arrive from the outskirts, they're read not as isolated anomalies, but as pieces from this larger picture. A sudden shift in dust impacts a subtle turn in the magnetic field, a gentle drop in the speed of the wind, a risen tide of cosmic rays. Each sign fits a story that began in the ashes of distant suns. The boundary born in starlight is therefore not an abstract idea. It is a prediction that guides instruments and routes. It tells where the wind should slow, where fields should twist, where dust populations should mingle, and where the interstellar medium should begin to speak louder than the sun. By placing the frontier within the long memory of the galaxy, the narrator sets the stage for what the farcraft will find: a draped field, a layered plasma, a shifting shield, and the soft echoes of storms that started far away. What follows is the effort to verify that story step by measured step, with long patience and with wonder, held steady as the probes inch toward the line that moves yet holds. He begins with a pair of lean, hardy machines that carry simple instruments, and an outsized patience launched when the dream of crossing the outer darkness still feels like an experiment. Pioneer 10 and Pioneer 11 leave the inner planets in the early 1970s under the care of the National Aeronautics and Space Administration, guided by the Jet Propulsion Laboratory, and heard by the Deep Space Network's widely spaced ears. Each carries a magnetometer to sense the bending of fields, particle counters to weigh the invisible rain of charged visitors, plasma sensors to read the speed and pressure of the solar wind, and detectors to register the soft taps of dust. Their first test is the asteroid belt, a region once imagined as a minefield, and they pass through with fewer strikes than fear, predicted a sign that the outer system will yield to careful travel. That calm is not emptiness. The instruments write a map where the lines are made of pressure and frequency rather than stone. The solar wind born in heat near the sun expands outward in a rolling breath. It is not steady. It carries streams where faster parcels overtake slower ones, and where their meeting forms extended ridges of compression that curl through space like long weather fronts. When Pioneer 10 moves outward, the telemetry shows these ridges as rises in pressure and field strength, followed by quieter intervals that are not truly quiet. The magnetometer reads a spiral field, wound by the star's rotation, and notes sector boundaries where the field flips its direction. These flips arrive with a rhythm that changes with the solar cycle, sometimes orderly, sometimes frantic, and this variability teaches the first lesson of the outer system time is as important as distance. When Pioneer 10 approaches Jupiter, the journey gains a new dimension. The giant planet is not only a world, it is a magnetic engine that carves a cavity in the wind. The craft sees the bow shock where the wind slows, and the magnetopause beyond it, and inside that border, a storm of particles trapped by the planet's field. The counters tick upward sharply, and the magnetometer records twists and drapes that look nothing like the interplanetary spiral. Auroral radio emissions hiss across the link as an indirect sign of voltages running along field lines. The lesson is that large worlds carry their own space weather systems, complex and dynamic, embedded in the sun's broader breath. Pioneer 11 later repeats the crossing and adds a passage by Saturn, where the magnetosphere is gentler yet equally structured, with rings acting as both source and sieve for dust and plasma. With the turns past, the giants complete the Pioneers re-enter the wind and continue the outward count. Far from the planets, the averages change. The solar wind slows on its long path, not in a single step but in a drawn decline as the flow picks up new ions that were once neutral atoms from interstellar space. These pickup ions add heat and mass and subtly thicken the stream. The plasma instruments do not see the atoms directly, yet they feel the effect in the pressure and the speed. The craft also ride through zones where turbulence seems to subside, and then to surge a pulse that lines up with these long spiral ridges launched near the sun. Each passage is a reminder that the outer reach is made of structures that extend for hundreds of millions of kilometers, so broad that a single crossing can last weeks, and so durable that the second craft coming later on a slightly different line finds traces of the same weather. Meanwhile, the cosmic ray detectors register a slow rise in high-energy particles. As the sun's shielding weakens with distance, more of the galaxy's charged messengers find their way inward. The increase is not uniform between the two paths. Latitude matters and time within the solar cycle matters, and the difference between the craft implies a bubble that is not a perfect sphere. The counts climb more steeply after certain solar minima and less steeply after certain solar maxima, as if the bubble's wall thickens and thins with the changing field near the sun and with pressure changes outside. This pattern plants the seed that later missions will nurture the heliosphere, has a lopsided living form shaped by the interstellar flow. The dust record contributes a second, quieter intrigue. Impacts do not fade with distance as a simple curve. At some ranges the rate holds steady. At others it dips. At still others it rises again. Approach directions matter. Grains from certain bearings and speeds appear more often, hinting that some are born from comets and collisions within the Kuiper belt, while others are interstellar visitors guided by charge and field toward preferred lanes. In the count, One can hear both the solar system's own slow grinding and the larger exchange with space beyond an early sign that the border will not be a sealed wall. The magnetometer logs add a steady drumbeat to these layered hints. Sector boundaries pass like pages turning, and long-lived interaction regions sweep outward like ribs in a fan. During active years, the spacing of pages grows irregular, and the ribs thicken. During quiet years, the pattern settles yet never becomes entirely smooth. The pioneers also record times when the magnetic field seems to align into a more uniform drape, and times when it becomes knotted and erratic. These moods will matter later near the place where the sun's wind gives way to the interstellar medium. Even their radio tracking leaves a puzzle that refuses to be forgotten. When analysts gather years of Doppler shift and range data to refine the paths, a tiny sunward acceleration appears in the equations constant in sign and steady across long spans. It is far too small to be felt by the craft, yet too persistent to ignore. For a while, the possibility that gravity itself may be whispering something new is allowed to stand because the numbers do not yield an easy cause. Later studies point to an uneven push from the craft's own heat, radiated preferentially in one direction, by warm electronics and power sources, a mundane answer that nonetheless carries its own wonder, because it shows how exact the measurements have become, how even the warmth of a box can buy us a path across the scale of a solar system. This episode becomes a parable for the frontier. Every anomaly is first an invitation, and every invitation demands careful patience before grand claims are made. Piece by piece, the two craft demonstrate that the outer reaches are not a gentle slide into emptiness, but a layered dynamic road. The slope of the wind's decline, the rise of cosmic rays, the patchwork of dust, the cadence of sector boundaries, the tidal push of interaction regions born near the sun, and the planet-made magnetospheres that dent and divert the wind, all combine into a grammar for reading what lies still farther out. Even their differences teach. The two trajectories sample different latitudes, and those differences echo through the counts and fields, suggesting a bubble that is pressed on one side, stretched on another, and constantly remade by both internal cycles and external flows. When their power finally wanes, and the deep space network must stretch to hear the messages grow faint but not trivial, what remains is a foundation. Future travelers will know to listen for plasma waves that can reveal density where particles grow too sparse to measure otherwise, to watch for subtle changes in magnetic direction that may signal a draped field at the boundary, to expect that cosmic ray rises will not be smooth, and that dust will not behave like a single population. The pioneers do not reach the heliopause, while their instruments are in full strength, yet they sketch its approach. They show a wind that weakens and warms, a field that organizes and tangles. By turns a sky where particles from the galaxy creep in with growing confidence, and a road where giant planets carve their weather into the larger flow. They send back a promise that the border is close enough to touch with the right patience, and that will not be a simple step but a set of layered changes, sharp in some ways and soft in others. In this way, the first far travellers map the unknown without finishing the drawing, and by leaving open edges they make room for the next craft to enter the frame and carry the story toward the line where the sun lets go. He turns to two craft built as twins, yet destined to read different poems from the same sky. Voyager 1 and Voyager 2 rise on separate days in the late 1970s under the care of the National Aeronautics and Space Administration, shaped by the Jet Propulsion Laboratory, and kept in touch by the Deep Space Network with patient dishes that trade whispers across a turning Earth. They launch toward a sequence of giant worlds that the geometry of that era briefly aligns, but behind the planetary portraits lies a quieter intention, long life in the dark enough power and discipline to carry magnetometers, plasma sensors, particle counters, dust detectors, and ears for natural radio across tens of billions of kilometers to the border where the sun's breath thins and another medium begins. Voyager 1 aims for Jupiter and Saturn and then tips north of the planetary plane. Voyager 2 follows to Jupiter and Saturn and then presses on to Uranus and Neptune before curving south. The split is deliberate. 2 latitudes, 2 sampling lines, 1 bubble to be mapped by comparison. Their earliest lessons echo the pioneers yet deepen them. At Jupiter, both craft feel the bow shock where the solar wind slows against the planet's vast magnetic shell, then the magnetopause, then the storming belts of particles trapped along field lines. The counters surge, the magnetometers twist from interplanetary order into planetary architecture, and radio instruments register auroral emissions that speak of voltages running like rivers along invisible rails. At Saturn, the patterns repeat with gentler strength, and the added signature of rings that feed and filter dust and plasma. At Uranus and Neptune, reached only by Voyager 2, the magnetospheres tilt and offset in ways that complicate models and leave the imprint of a symmetry that will later matter at the edge. The grand tour ends as the enduring mission begins. Beyond the giant planets, the solar wind becomes a long and patient slope. It is no longer the brisk flow of the inner system. It has picked up heavy passengers. Neutral atoms from the local interstellar cloud drift inward across the boundary, lose electrons under sunlight or in collisions, and become pickup ions that the wind must carry. With every pickup, the wind warms and slows, and its pressure changes in ways that the instruments can feel even before the particles themselves are counted. The spiral magnetic field wound by the sun's rotation loosens with distance and flattens with latitude. Voyager 1, climbing northward, records sector boundaries, where the field reverses with a rhythm that stretches and compresses a sign that the long ridges and valleys born near the sun broaden and overlap. Voyager, 2 southward bound, crosses a different sequence of ridges, and by laying the 2 records side by side, the team see that time and latitude weave together, that the outer system cannot be read by distance alone. The particle counters add a layer of weather that is neither cloud nor wind. High-energy cosmic rays seep inward in greater numbers as the sun's shielding weakens with distance. The increase is not smooth. It steps, pauses, and surges with the solar cycle, and with the passage of shocks launched by eruptions closer to the sun. At times the counts change without an evident solar cause, and the mismatch between the 2 voyages hints that the heliosphere is not a uniform ball, but a shape pressed by an external flow and bent by an external field. Dust detectors contribute a quiet pattern of taps that refuses a single origin story. Some grains arrive from bearings and speeds that mark them as members of the solar system chipped from comets and ground by collisions in the Kuiper belt. Others approach along lanes that are better explained by visitors from interstellar space, guided by electric charge and magnetic field toward preferred paths. The mixture suggests exchange across the border, a porosity that will matter when the Voyagers reach the threshold itself. The plasma instruments meant to read speed, density, and temperature directly age differently on the 2 craft. On Voyager 1, the main plasma sensor falls silent after the planetary tour, leaving a gap that would be ruinous if not for another tool. A plasma wave instrument listens to faint natural tones that ring in the sea of electrons. From the frequency of those tones, the teams can infer density. This substitution turns sound without air into a ruler, and when shocks pass, the sudden ringing makes the ruler easy to read. On Voyager 2, The primary plasma detector continues to work, providing direct measurements that anchor the inferences from the musical method. Together they form a pair of ways to count the medium, and later, beyond the boundary, they will combine to reveal where the sun's wind finally ends. The outer sheath announces itself as a place rather than a number. Far from the sun, the long slope steepens and a shock is crossed. The termination shock is not a knife edge, it is layered and shifting. Voyager. 2 senses a clear drop in wind speed and a jump in temperature, the classic signatures of a shock. Voyager, 1 lacking direct speed readings, instead notes changes in turbulence and the wandering of the magnetic field. Immediately beyond lies the heliosheath, a region of slowed, heated wind that should be a cushion, but behaves like a restless sea. Pressure balances are uneven, flows are lopsided, eddy and ripple refuse the comfort of symmetry. Magnetic draping becomes a theme. As the heliosphere presses outward, it meets an external field that cannot be ignored. The magnetometers record a trend toward a more constant orientation, as if the outside fabric is pulling the inside threads into alignment. The expectation grows that a crossing into the interstellar medium will bring a strong turn in direction, but this is precisely where the data complicate the story. When the first step is taken across the heliopause, the change that shouts is in particles, not in direction. The density of low-energy solar particles falls, the count of high-energy, cosmic rays rises, and the inferred electron density matches interstellar values, but the magnetic direction turns only modestly. A boundary that is sharp in species behaves as if it is blurred in angle. Voyager 1 reaches this threshold first, and writes the date into the ledger as a turning of an era. Years later, Voyager 2 crosses at another latitude and records a similar set of steps, with the added clarity of a functioning plasma detector that shows the inner wind as slower and hotter, and the outer plasma as cooler and denser. The 2 passages together transform argument into outline. The heliopause is a contact between media where diffusion of particles is limited, but magnetic geometry folds in complex ways. Radio tracking itself becomes an instrument that speaks about the road. The deep space network times each signal to fractions of a heartbeat and notices tiny twinkles caused by plasma irregularities along the line of sight. These scintillations vary with solar cycles and with the arrival of large shocks, and by reading them the teams place disturbances between the sun and each craft like markers on a moving map. As power falls, the choices grow more severe. The teams turn off instruments one by one to keep the most telling sensors alive. They keep the magnetometers, the particle counters, and the radio ears. Heaters are rearranged to keep valves from freezing. Voltages are trimmed. New operating modes are tested with caution. Each saved watt is a year, and each year is a chance to watch the heliosphere breathe as it answers pressure from the outside and pulses from within. By the time the twins have travelled many tens of billions of kilometres, their portraits of the edge converge on several truths and open a broader ring of questions. The wind slows and heats before stopping. The boundary in particles is sharp even when the magnetic direction is not. Cosmic rays flood in beyond the border with fresher confidence. The bubbles' size and shape vary with latitude and with time, yet how strongly the interstellar field drapes, how tangled it becomes in the sheath, how permeable the magnetic wall is to different energies, and how shocks from distant stars echo through the border, remain open lines in a poem still being written in very slow ink. He turns the lens inward again, not to the inner planets, but to a craft that runs between worlds like a stone thrown with deliberate aim. New Horizons leaves Earth in the year 2006 under the care of the National Aeronautics and Space Administration, built by the Johns Hopkins Applied Physics Laboratory, with partners at the Southwest Research Institute, and held in touch by the Deep Space Network, that spreads on 3 continents to keep the Whisper alive. Its first public rendezvous is Pluto in the year 2015, then a small contact binary in the year 2019, but the tale he follows is about the years before and after, when the craft moves through the Kuiper Belt and reads the dark between the scattered suns. The mission carries a long camera called the Long Range Reconnaissance Imager that sharpens the horizons of faint targets a colour, an infrared mapper named Ralph that paints the cold surfaces a far ultraviolet spectrograph named Alice that hears the thin gases, a solar wind analyzer that sniffs the outflow from the sun, an energetic particle spectrometer that weighs the harder rain, a radio experiment that uses Earth's round trip echo to sound atmospheres and refine gravity maps, and a dust counter built by students that feels the taps of grains along the path. It also carries star trackers, whose quiet purpose is to steady the craft by reading faint patterns in the night, and in that reading a second life emerges, the star trackers become a census taker for the faint glow that lies between the points. Before the flyby of Pluto, the instruments build a long baseline of the outer system's texture. The solar wind near Jupiter still carries strength, but after the gravity assist that bends the path and deepens the speed, the readings show a steady decline as distance grows. At many billions of kilometers from the Sun, the flow is less crowded and slightly cooler, yet punctuated by long pressure ridges borne closer to the star. The energetic particle instrument counts a blend of injected particles from solar storms and a freshening drizzle from interstellar space that the waning shield allows to approach. None of the curves are smooth, and the cadence along this line adds one more strand to the map the earlier craft began. The student dust counter is the quiet star of the cruise. Impact after impact, or sometimes long runs with no impacts at all, it traces a population that refuses simple predictions. Models once imagined a rising curve of dust counts into the Kuiper Belt fed by collisions among countless small bodies, but the meter instead records a modest level that stays surprisingly flat with distance, and even dips in some stretches as if the grinding is slower than expected, or the grains are being swept aside by subtle forces. Approach direction matters. The counter sees more taps from lanes aligned with the sun's motion through the local cloud, and fewer from others, a hint that charged grains from interstellar space are funneling along preferred routes while local grains drift more lazily. In this one instrument, the border's porosity glows into view. The solar system is not sealed, and exchanges happen grain by grain, across a frontier that is moving and thin. When Pluto rises in the field, the outer space becomes local again. The solar wind analyzer reads how the wind struggles against a small world that leaks a thin atmosphere of nitrogen and methane. Pickup ions appear where neutral atoms stripped of electrons are caught and thrown by the magnetic field embedded in the wind. The shape of the interaction is neither a full magnetosphere nor a naked rock. It is a hybrid, a comet-like wake that drapes behind a dwarf planet. This portrait matters for the border story because it shows how scale and environment intermingle. Even modest gas release in the Kuiper Belt can seed hot pickup ions that add to the load the wind must carry, and these additions accumulate into the larger pressure picture that sets the sheath and the boundary farther out. After Pluto, the craft enters a region where the giants no longer shape the wind, but where the collective gravity of many small bodies and the distant pull of Neptune still sculpt the traffic of dust and ice. The star trackers and the long camera scan the sky for faint smudges to choose a second target. In that search, the mission refines the positions of many background stars and measures the sky glow that lies between them. By comparing images taken when the craft is far from the bright haze that surrounds Earth with images taken by space telescopes in near-Earth orbit, The team argues that the diffuse light between galaxies is lower than some earlier estimates, as if the universe is a little darker between its islands than expected. He does not need a firm conclusion to feel the wonder. He needs only to note that a probe meant to study nearby ruins can also weigh the faintest background where creation's spillover should lurk. Between the encounters, the radio experiment deepens its role as a ruler. The carrier tone from Earth and the echo back pass through a medium that leaves tiny fingerprints on frequency and phase. By reading those prints, the team can refine the gravity field near Pluto, and later near the small contact binary, but also sense the gentle noise of plasma along the line of sight. Over long years, the Deep Space Network's timekeeping beats like a metronome. When shocks launched from the sun pass, the craft the phase wanders in a way that can be tied back to events nearer to Earth. In this way, the mission's thread through the Kuiper belt becomes a recorder of the sun's long breath, and a witness for how those breaths weaken and break into patches. The particle instruments add to this by catching the tail ends of solar storms long after they have lost their violence. They arrive as muted waves, still visible as rises in energy and number, still enough to make the dust counter's rate shift, as charged grains are nudged to different paths. Against this changing foreground, the mission keeps its attention on the slow background. The Kuiper belt is not only a mine of objects, it is a laboratory for how ancient water ice organics and rock preserve themselves in a cold so deep that common chemistry stalls. By measuring colours and spectral bands, the instruments see surfaces coated with methane nitrogen and complex carbon chains that have been processed by cosmic rays for billions of years. The brightness patterns and the craters count the ages of collisions, and the distribution of sizes sketches a population shaped by quiet grinding rather than violent unrest. The belt seems calm compared with the heavy traffic of the inner system's ancient youth, yet its calm hides a gentle but persistent exchange. Grains split off and spiral inward under sunlight. Electric charges steer paths and slow drifts across resonance lanes. With Neptune deliver some migrants toward the inner regions, while others are gently parked into colder storage. In these patterns, the mission reads the conditions that the heliosphere's outer layers must answer. The solar wind flowing through this debris field picks up ions and dust. Its magnetic field drapes around small obstacles. Its pressure is modulated by long waves born in cycles at the sun. Each of these acts like a small vote in the grand balance at the edge. Thus, when he says New Horizons brushes the belt, he means that the craft does more than take pictures of worlds. It samples the quiet foreground that stands before the boundary maps. The dust that may pierce and mingle across the border listens for tones that reveal plasma density where other instruments fall silent, and times the arrival of distant shocks that march outward into the sheath. It even weighs the darkness between galaxies by using the simple honesty of a camera set far from the sun's glare. The intrigue is that a mission built for near targets ends up sketching a grand backdrop, a stage on which the heliosphere's edge is set to play. The star trackers that steady the craft also measure the faint light that fills the void. The dust counter, once meant as a student's lesson, becomes a primary witness for the economy of grains in the deep. The radio tones used for navigation become a subtle probe of the medium. Through these many small readings, the boundary grows less like a line on a chart and more like a living margin, with suppliers' drains and long-draped curtains that respond to pressure from both sides. The path continues beyond the second rendezvous, and the instruments trimmed and conserved keep building the slow record. As power declines, the choices sharpen, yet the pattern is clear. The Kuiper belt is a quiet forecourt where the sun's wind gathers charges and grains, and where the balance of pressures sets the tone for what the Voyagers would later meet. He sees in this cruise a subdued drama, a dim field of dust that does not quite match early expectations, a sky glow that may be darker than first thought, a wind that ebbs and swells with long waves, and a long measurement that connects inner storms to outer murmurs. From this, the shape of the coming threshold becomes a little less opaque, not solved but more finely outlined by the slow testimony of a craft that was built to pass quickly through, and yet ends up teaching that the quiet in between is where the story begins to gather depth. He turns to the quiet rain that does not look like weather and does not shine like starlight. He turns to dust because the smallest pieces travel the farthest and remember routes that larger bodies forget. A grain in deep space is not a speck of dirt. It is a tiny ship with an electric charge, a thin skin of chemistry and a history written in scars. Its path curves under gravity, under the gentle push of sunlight, and under the long hand of magnetic fields that thread the solar system and the interstellar medium. The instruments that greet it are patient plates and thin films that feel an instant when a grain strikes and turns to vapor, leaving a pulse that can be weighed for speed, for mass, and for direction. With such simple ears, the far craft learn that dust comes from more than one ocean. The pioneers carry early counters that click at a rate which does not fade as quickly as a simple model would promise. The Voyagers add years of taps whose approach angles do not match the traffic lanes of comets alone. New Horizons brings a student-built sensor that counts with steady resolve across the Kuiper belt, and hears patterns that bend away from easy expectations. The picture that gathers across these records is a mixture. Some grains are born here from collisions among frozen bodies and from slow erosion under sunlight. Some arrive from beyond the sun's domain, guided by charge and field, along preferred lanes that do not care about the planetary plane. He explains how charge turns a speck into a compass needle. Sunlight shakes electrons loose. The solar wind and the thin bath of ultraviolet light swap charges again and again. A grain that would fall one way under gravity alone now feels a sideways pull along magnetic lines. Those lines spiral with the rotation of the sun and drape where the heliosphere presses into the interstellar medium. As a result, the allowed paths for charged dust form corridors that widen and narrow with the solar cycle, and with the pressure of the cloud outside. The counters hear this geometry as a rhythm. During years when the sun's field strengthens, certain lanes thin and the upwind approach weakens. During quiet years those lanes refill and the upwind count grows. The phase of that rhythm matches the rise and fall of cosmic rays and the waxing and waning of pickup ions, so that dust ions and high-energy particles become three voices singing the same cycle in different keys. He listens for directions because directions carry the proof of origin. Local grains tend to follow the slow traffic of the Kuiper belt, with many arrivals near the planetary plane, and with speeds that fit a home-born drift. Visitors from beyond prefer bearings that line up with the flow of the local interstellar cloud and with the orientation of the draped field. They arrive from higher latitudes in surprising numbers and with speeds that do not match any family of comets. The ratio between these two populations is not fixed. It changes with time and with distance, and the changes themselves say that the border is porous and alive. He spends time with New Horizons because its long cruise through the Kuiper belt turns subtle differences into a map. Before that mission, models favoured a rise in dust counts outward, as collisions among many small bodies should feed a thicker haze. Instead, the rate remains modest, almost flat through great spans and even lower in some reaches, as if slow grinding has grown quiet or as if grains are being guided away. The approach angles in those same reaches lean toward bearings that fit interstellar lanes more than local ones, adding weight to the idea that the field and the sun's motion through the cloud pick winners among the many possible paths. He remembers that not every stranger is interstellar. There are storms of small fragments born near the sun and launched outward by sunlight and by field into high latitudes. These swift migrants, called in common language the tiny light-driven meteoroids, appear more often when the solar magnetic pattern favours open routes and thin when that pattern flips. They are local by birth, yet foreign by behaviour, proof that any simple label can mislead at the edge where forces braid. He speaks of chemistry because the skin of a grain is a notebook. A traveller that spends millions of years in cold shadow gathers thin coatings of hydrogen-oxygen, carbon-nitrogen, and rarer companions that freeze upon contact. Cosmic rays with long reach cross its surface and rearrange bonds into darker and more complex films. When such a messenger crosses the heliopause and enters the warmer, more variable radiation field inside its skin, slowly changes again. The difference between those two skins is a timestamp. Larger grains seen by scattered light and rare grains sampled by collectors near Earth both hint at such histories, and the counters out in the dark supply the missing context by telling how many travellers pass, from which directions they come, and how those numbers swing with the mood of the sun. He adds the way dust and plasma trade identities across the border. Neutral atoms from the cloud drift inward and become ions when sunlight or collisions strip electrons. Those newly charged particles are picked up by the solar wind and add heat and mass. Grains carry out a similar exchange in reverse. Charged grains that ride the draped field can become neutral when they lose charge through contact or through radiation, and in that state they can pierce deeper where a charged path would have curved away. Then they charge again and rejoin the disciplined lanes. The result is a constant swapping that makes the frontier less like a wall and more like a lace. The counters hear this as slow seasonal change and as sudden shifts after strong shocks pass outward. A shock from the sun can narrow or widen the magnetic drape for months, closing a corridor here and opening another there so that dust that does not belong in the simplest picture appears then fades. He turns to gravitational focusing because gravity still writes gentle accents into the score. The flow of neutral atoms from the interstellar cloud bends around the sun and forms a downwind cone of slightly higher density. Charged dust fills fields first, yet larger, and less charged grains can ride that focus stream, and when the counters sweep through the downwind side of the solar system, the rate of taps grows a little late, proof that even far from planets the sun shapes the traffic in delicate ways. He notes that radio itself becomes part of the dust story. When shocks roll outward, the deep space network hears a faint wandering of signal phase, caused by ripples in electron density along the line of sight. Around those times the dust rate often shifts, as well as if the same disturbance has guided charged grains into or away from the craft's path. Sometimes the correlation is immediate, sometimes it lags by weeks, and the variety hints at a layered border in which a fast front changes the lanes quickly, while slower draping evolves afterward. He keeps one lesson close: the phrase "dust that does not belong" is a mirror that reveals a broader belonging. The solar system breathes outward through the heliosphere, the interstellar medium presses inward with its own weather, and the edge between them is a moving net that catches and releases. Grains from outside are not intruders. They are messages from distant furnaces and cool clouds, carrying surfaces shaped by ages in dim light. Grains from inside that rush outward are not waste. They are seeds that write the sun's presence into the larger cloud. The counters on patient plates, the faint flashes on wide cameras, and the rhythm of radio during distant storms combine into a quiet revelation. The border is a marketplace where matter trades charge and direction, where lanes open and close with the sun's cycle, and with the pressure of the surrounding cloud, and where the simplest specks behave like disciplined travellers obeying rules that are invisible but not unknowable. From those travellers the far craft learn that the frontier will not be drawn by a single step, but by a braided set of flows, some born here, some born far away, all telling that the heliosphere is not a sealed shell, but a living margin that sifts sorts and speaks. He listens to the breath of the sun far from its face, and hears a change that is both gentle and relentless. Near the star, the solar wind is a bright rush of charged particles, a river of protons and electrons that race outward and carry the sun's magnetic field, like threads wound into a spiral. With distance that river tires. It gathers passengers, it spreads, it cools in fits rather than in a smooth fade, and the field that rides within it begins to twist and tangle in ways that reveal both the memory of the star's rotation and the pressure of the space beyond. The voyagers, the pioneers before them, and the craft that move more slowly in the Kuiper belt all show this same story with different instruments. The wind weakens not as a uniform slope but as a staircase whose rises are made by interaction regions launched near the sun when fast streams overtake slower ones. Each interaction grows into a coiling front that thickens the magnetic field and compresses the plasma. Those fronts stretch over hundreds of millions of kilometers so broad that a single crossing takes weeks, and so enduring that one craft can step through the afterimage of a front that began when the sun wore a different mood. Between fronts the wind seems calmer, yet even the calm is threaded with waves. The magnetic field far from the star is a spiral whose angle steepens with distance, a form often called the Parker spiral, and within that grand curve the field flips its direction sector by sector, as the sun turns and its magnetic poles wander with the cycle. Near the inner planets those flips come like a regular page turn. Farther out the pages become uneven. Boundaries smear as turbulence grows, then sharpen in unexpected hours, as if the wind has become a patchwork quilt stitched by events from months before. The voyagers feel this in the magnetometers as sudden turns between outward and inward field lines in the plasma readings as changes in speed and density, and in the particle counters as rises in low-energy ions where compression heats and traps them. Over time, the average speed trends downward. Pickup ions born from neutral atoms in the local interstellar cloud add mass that the wind must carry, and to carry that mass the wind surrenders speed and accepts warmth. The heaters are not coils, but processes wave particle interactions that rattle the ions and convert directed flow into random motion. The plasma becomes less like a streaming river and more like a churning sea. Yet the weakening is not only an interior tale. Outside the heliosphere lies a magnetic field not of the sun's making, and a pressure born of gas field and cosmic rays in the nearby cloud. Where the outward push meets the inward press, draping begins. The sun-spiraled field lines near the edge are pulled into new alignments by the external field. The result is a region where the field seems to lose some of its rotational memory and adopt a gentler, steadier direction. That steadiness does not announce itself as a clean rotation at a single distance. Instead, the data show corridors of ordered field nestled among bands of turbulence, a braided approach, rather than a march toward a wall. In those corridors, the field direction holds for longer spans. The particle populations shift and the plasma density inferred from the faint ringing of natural waves creeps toward values that belong to the medium outside. Where turbulence returns, the direction jitters, and the plasma seems warmer and less dense again. He imagines this not as a simple shell, but as a weathered shoreline with inlets and sandbars that steer the flow. The weakening wind also carries the sun's long cycles outward, like encoded pulses, a maximum near the star with spots and flares and coronal mass ejections sends a train of shocks. These travel for years and shake the outer wind, thickening the interaction regions and fattening the segments where the field is compressed. A minimum sends fewer, and the road quiets. The Voyagers register these changes as prolonged rises in magnetic pressure, as clusters of field reversals, and as steps in cosmic ray counts that move in response to the moving barriers. Beyond the termination shock, where the supersonic wind first stumbles and becomes subsonic, the weakening becomes a structural change. The heliosheath, that broad cushion of slowed and heated solar wind, is expected to smooth the transition, but the readings tell a more restless story. The flow is lopsided. Pressure is not balanced neatly between particles' magnetic field and any unseen components. One side of the bubble appears pressed more firmly than the other, and that press varies with time, implying that the local interstellar medium does not merely sit but moves and morphs. Within the sheath field lines may fold back on themselves. Magnetic reconnection, the process by which field lines break and splice in new pairings, could be at work opening channels where particles of certain energies sneak across what would otherwise be a stricter boundary. The particle counters suggest such selective permeability for the rise in cosmic rays is delayed in some energy ranges and quick in others, an energy-dependent weather that would be natural in a layered reconnecting sheath. He considers the surprising modesty of the field rotation measured at the heliopause. A textbook expectation would ask for a strong twist when stepping from the sun's spiral into the external field. Instead, Voyager 1 records only a modest change. Voyager 2 with a working plasma instrument confirms the particle and density step while also finding only a limited rotation in direction. The weakening wind meets its match in a scene where geometry does not switch like a binary. Perhaps draped field lines from the outside have already infiltrated the sheath over great distances, training the inner lines into partial alignment well before the actual contact. Perhaps ripples on the boundary mix directions in a way that averages to a small turn even when local angles are sharp. Perhaps the boundary is not a single surface, but a set of nested sheets that a craft crosses over days, smoothing a sharp turn into a slow roll. In any case, the twisting of the field at the edge is subtler than the sharp drop in solar particles and the sudden rise in ambient electron density. The weakening wind then is not only a fade of speed, it is a change of rules. An instrument that is suited to read cold fast ions finds itself reading warm slow ones. A magnetometer that once traced a clean spiral begins to sketch a script with loops and crossings. A particle counter that once saw solar material in command now records a chorus in which the galaxy sings louder. The speculative line that emerges is simple in phrasing, yet rich. In consequence, the heliosphere's edge is not a static bumper but a flexible joint. When pressure outside rises, the joint tightens. When it falls, the joint loosens. When the sun cycle swells, the joint is toned by waves and shocks. When it ebbs, the joint relaxes and allows more cosmic material to drift inward. Long-term drifts in the local interstellar cloud, perhaps pockets of slightly denser gas or patches, where magnetic tension is higher, could further bias the joint toward one side, leading to a bubble that is squashed here and elongated there. He thinks of how these changes cascade inward. A tighter joint allows more breaking of incoming cosmic rays, a looser joint less. Over centuries, such modulation could leave fingerprints in the chemistry of planetary upper atmospheres, or in the rates at which certain isotopes form in air and ice. Those are ancient records compared with any mission span, but the principle links the far edge to inner weather, with an elegance that fits the larger pattern. The sun breathes, the wind weakens, the field twists, and the distant medium pushes back. The craft hear all this as faint variations in tone, as minute turns of a magnetic needle, as counts stepping up or stepping down by small fractions, and in those small signs they read a grand hinge that never stops moving. He enters the Helios sheath, the long cushion beyond the termination shock, where the solar wind is no longer supersonic, and where simple pictures of a smooth decline yield to a landscape of crowds, eddies, and unbalanced books. Here pressure should spread evenly among warm ions, magnetic field, and particles of many energies, yet the readings refuse that neat ledger. Voyager 2 sees a drop in speed and a jump in temperature at the shock, as theory suggests, but beyond that step the flow behaves like a restless sea. Patches of high magnetic pressure sit beside lanes where the field relaxes, and between them the plasma sloshes, sometimes even turning sunward for hours before resuming its outward crawl. Voyager 1, without a working direct plasma sensor, listens with its plasma wave instrument and hears tones that reveal electron density rising and falling in broad swells, as if the sheath carries internal weather that shifts over distances of billions of kilometers. In some segments, the magnetic field aligns into extended stretches that feel ordered, as though the external interstellar field is already training the inner threads. In other segments, the needle jitters from one moment to the next, and the order dissolves into noise. The counters for low-energy particles tell a complementary tale. Just beyond the shock, ions that once rode with the wind are heated and trapped, forming a population that holds significant pressure. Farther out, their dominance wanes, while higher energy particles begin to speak louder. The cosmic ray counts climb in a slow crescendo, punctuated by steps when broad compressions pass. Sometimes the rise is delayed at certain energies, sometimes it leads a staggered choreography that hints at channels opening and closing for different particle sizes. This energy dependence is a natural language for a region where magnetic reconnection may splice and reshape field lines, creating selective corridors where some particles cross while others are turned aside. Pressure balance expected to smooth the ride becomes instead a source of structure. Where magnetic pressure strengthens, thermal pressure often dips, and where thermal pressure swells, the field slackens, but the trade is imperfect. The ledger does not quite close unless one admits a hidden term, perhaps pressure carried by particles too energetic for local instruments to catch, perhaps tension stored in twisted fields, perhaps waves that carry momentum without showing plainly in counts of particles or in static field readings. The result is a sheath that is not merely hot and slow, but compositionally complex, a stew whose flavour changes with latitude, with time, and with the long pulse of the sun. Flow lines are not straight. Measurements of the direction of plasma motion show surprising deflections sideways and away from the expected radial course, and at times there are hints of backflow. Such detours can form when pressure gradients build along the flanks, when the external medium presses unevenly, or when narrow jets created by reconnection squirt energy into preferred directions. The image that rises is of a borderland where the sun's wind, robbed of its youthful speed, becomes prone to being herded by weak nudges and subtle slopes, so that even small contrasts in field or density can deflect the stream. In this same zone, Voyager 1 reports episodes of unusually quiet magnetic fluctuations, stretches where the field points with rare steadiness, and where low-energy solar particles nearly vanish, even though higher-energy particles from the galaxy are still rising. Those intervals have been called passages along magnetic highways, for they feel like lanes where field lines connect more directly to the interstellar medium and allow particles to trade places with less hindrance. If that reading is right, then the helios sheath contains layers where connectivity to the outside is briefly strong-nested among layers where it is weak, turning the approach to the heliopause into a weave rather than a wall. Remote sensing from the inner system supports the complexity. The Interstellar Boundary Explorer maps energetic neutral atoms, which are born when fast ions steal electrons from neutral atoms, and thereby become fast neutrals that fly in straight lines. By measuring how many such neutrals arrive from each direction, the mission sketches pressure and particle populations at the boundary from afar. The maps reveal a bright narrow ribbon arcing across the sky, brighter than surrounding regions and aligned not with planetary planes, but with the direction of the interstellar magnetic field draped over the heliosphere. That ribbon shifts with the solar cycle, and with large shocks that sweep outward, implying that the sheath and the immediate exterior respond together to both inner and outer pressures. The ribbon's very existence argues that magnetic geometry is sculpting where charge exchange is most efficient, and therefore where trapped ions pile up and where the sheath's currents concentrate. Closer to the heliopause, the plasma wave instrument on Voyager 1 becomes a seismograph for a membrane. When a strong solar eruption launches a shock years later, the sheath rings as that front passes, and the tone reveals how dense the electrons have become. These tones show discrete steps upward in density across spans of weeks, as if the craft crosses nested layers of increasingly interstellar character. The steps are not evenly spaced, and the heights vary, which fits a boundary with folds and ripples rather than a single mathematical surface. Voyager 2, with its direct plasma instrument alive, adds the missing temperatures and speeds to these sonic inferences, and confirms that the outermost layers cool and thicken in ways that match a transition to the interstellar medium. Yet for all this converging evidence, the magnetic direction turns only modestly at the final step, a subtlety that deepens the strangeness. Perhaps the heliosheath has already trained the inner field to drape along the same chords as the exterior, minimizing the final twist. Perhaps the boundary is corrugated so that a craft averages sharp local rotations into a gentle overall bend. Perhaps reconnection stitches inner and outer fields into a patchwork that looks aligned on average, while remaining ragged in detail. Pressure from outside is not still. The local interstellar medium is a warm, rarefied cloud moving relative to the Sun. Its magnetic field has a definite orientation and tension. Pulses from distant stellar events, long faded but not erased, occasionally drift through. Each factor nudges the sheath. The bubble's nose may compress while the tail stretches, then later the pattern may soften. Such changes turn the heliosheath into an archive of both inner cycles and outer tides, preserved as subtle shifts in flow direction, as temporary corridors of connectivity, as moving pockets where certain energies of particles are favoured. Even dust counted as taps on distant plates follows this choreography, with rates that rise when corridors open and fall when they close, offering a tiny but telling echo of the larger plasma dance. In this place, the speculative question grows sharper. What unseen actors hold the missing pressure and shape the lanes? The candidates each open their own doorways. High-energy particles above the main detector ranges could quietly stiffen the sheath. Tangled magnetic fields storing tension that is released through reconnection could power jets and carve channels. Waves that carry momentum might transport energy outward, without leaving easy fingerprints in the averages. The truth may be all of these in changing proportions. That variety would explain why two craft probing at different latitudes and at different times read the same overall story but with distinct accents. He ends the passage through the heliosheath with a feeling that the Sun's borderland is not a static cushion, but a living estuary where two fluids meet and mix under winds that change with seasons and under tides that come from beyond the horizon. Pressure refuses to balance in any one currency. Lanes of exchange open and close on scales of months and years, and the final approach to the interstellar medium becomes a braid of ordered corridors and tangled eddies. The anomalies are not flaws in the picture. They are the picture evidence that the heliosphere relaxes its grip through a complicated give and take, rather than a single surrender. What waits beyond the heliopause is hinted at in the rising electron density and the growing confidence of cosmic rays, but the sheath's strange behavior warns that the next step will not erase the sun's influence. It will recast it into new terms, and those terms are still being written by slow instruments under a wide and patient night. He listens for a kind of sound that does not travel by air and does not shake any human ear, a sound that lives in the sea of charged particles and reveals itself as a rhythm in electric fields. Plasma is a state of matter in which electrons and ions move freely, and in that sea there are natural oscillations like ripples in a pond that occur when the electrons are disturbed and then pull back toward balance. The frequency of those oscillations depends on how many electrons are crowded into a given volume, so a measurement of tone becomes a measurement of density. The distant craft carry instruments that can hear these faint oscillations as changes in voltage, and because these tones fall into ranges that can be sent to Earth and displayed as simple lines on a graph, the teams turn plasma into music and music into a ruler. This becomes especially important when some direct plasma sensors age out, because then the ringing of the medium itself becomes the only way to count the electrons. The method works like this. A shock from a strong eruption near the sun travels outward for years. It pushes and compresses the plasma ahead of it, and when it passes a spacecraft, the electric field trembles. The plasma wave instrument records a burst at a characteristic frequency that depends on electron density. The teams read that frequency, convert it to a density using a simple relation, and mark a point on a long timeline. If another shock arrives months later, there is another burst and another point on the graph. In time, a ladder of points rises, each one a note that says how much the plasma has thickened or thinned along the path. When this ladder is drawn across the region just inside the heliopause and across the region just outside of it, a pattern appears. Inside the heliosheath, where the solar wind is slowed and heated, the electron density is relatively low and variable. Just beyond the heliopause, where the interstellar medium begins, the density steps upward to a value that remains higher on average, with local swells and dips riding on top. This step is one of the clearest signs that the craft has entered a new medium, even though the magnetic field direction turns only modestly. It is as if a traveller leaves a light mist and steps into a fog that is still thin by any earthly standard, but measurably thicker than the air before. The beauty of this method is that it requires no steady stream of particles to strike a detector. It relies instead on the medium's own reaction to a passing disturbance. This is why it succeeds at great distances where the solar wind has dimmed and direct sensors struggle. It also turns the timing of solar storms into a tool. The National Aeronautics and Space Administration tracks strong eruptions near the Sun, follows their progress through the inner planets, and anticipates their arrival at the outer craft years later. When radio tracking shows that a front has reached a certain radius, the teams watch for a burst of plasma tones. When one appears, they make the density estimate and then combine it with magnetic field readings and particle counts to build a fuller picture of the local state. In this way, the planets become like stations on a railway timetable: the Sun, the origin of a train of waves, and the heliosphere, the long track where each passing car rings the line it rolls over. The distances are great, the energies are lower by then, but the tones are still clean enough to be heard across the long silence. Occasionally the instruments hear a hiss rather than a sharp note, a broader band of activity that hints at turbulence or at multiple small disturbances overlapping. Even that hiss can be instructive because it tells that the plasma is not smooth but ruffled, that there are gradients and small waves carrying energy through the sheath. In some intervals, the tones grow stronger and more frequent, matching periods when the sun has been active in the years before, and in other spans the line quiets, reflecting a calmer star. The density estimates on both sides of the heliopause also vary with latitude between the two Voyager trajectories, confirming that the outer medium is not perfectly uniform and that the bubble's boundary is crumpled in ways that concentrate or rarefy electrons over distances of billions of kilometers. He notes another virtue of listening. The plasma wave instrument does not only respond to shocks, it can also detect more subtle whispers caused by the drift of electrons along magnetic field lines and by the conversion of energy from other types of waves. These quieter features help map how energy moves in the sheath and in the interstellar medium, just beyond revealing whether the region is storing tension in fields that then unwind, or if it is constantly dissipating energy in small bursts. At times, the instrument records a series of short discrete tones that climb in frequency over days, a pattern that can be read as a shock slowing, and the compressed plasma relaxing like a struck bell, slowly losing its high overtones. In other cases, there is a sudden jump to a higher frequency that stays for weeks, a clear sign that the craft has crossed a boundary into a denser layer. Those steps often occur near other telltale changes. A drop in the count of low-energy solar particles, a rise in the count of higher-energy cosmic rays, and a tempering of magnetic turbulence. Together these signs make a layered portrait of the edge. The listening is delicate work. The instruments must be kept free of electrical noise from their own spacecraft. Heaters and switches are managed to avoid contaminating the measurements. The deep space network's timing must be steady to within tiny fractions of a second to capture the exact signature of each burst. The effort pays off when a sequence of tones allows the teams to draw a profile of electron density across a boundary that no camera can see. When the final step beyond the heliopause is inferred from a consistent set of higher density tones, there is a satisfaction that comes from translating invisible music into a map. The map is not static. Years after crossing the craft, continue to hear distant shocks arriving from the inner system. The notes still ring, and the measured densities vary moderately, which tells that the local interstellar medium is not an empty vault, but a living place where pressure waves travel, and where the imprint of the sun's breath remains audible beyond the border. At the same time, unexpected silences occur. There are spans when few shocks arrive and the tones quiet, leaving a baseline that describes the undisturbed medium. Those baselines are as precious as the bursts because they answer the simple question of what the background density and turbulence are when no large disturbances are passing. He lets the mind drift to a speculative shore. If the local interstellar cloud contains pockets of slightly different density, then as the heliosphere drifts through them, the average tone should drift as well. Over decades, the baseline could rise or fall, and with it the balance of pressure across the heliopause would change. A denser patch would push inward, perhaps altering the shape of the bubble and the lanes along which particles exchange. A thinner patch would relax the press, perhaps opening easier routes for certain energies. The plasma wave instrument would then serve not only as a boundary marker, but as a long-range weather station reporting the slow tides of the larger cloud. The technique also invites comparison with maps made from Earth orbit that record the flux of energetic neutral atoms born at the edge. When both methods agree on where pressure piles up and where it thins, confidence grows that the draping of the magnetic field is channeling energy into preferred arcs. When they disagree, the gap points to missing physics, perhaps a role for very high-energy particles that the local instruments do not count, or to transient folds in the boundary that one method averages away while the other catches. In all of this, the humility of the approach stands out. No grand telescope views the edge. No picture is returned of a glowing shell. Instead, there is a series of tones, sometimes sharp, sometimes broad, each one a whisper that must be weighed and placed. From those whispers, the teams learn that the interstellar medium just beyond is denser than the sheath that the boundary is layered, that shocks from the sun can still be heard far outside, and that the magnetic field's geometry plays a quiet but decisive role in how those sounds travel. The result is a kind of cartography by echo, a map drawn from the way the sea answers a distant hammer. It fits the broader story because it turns absence into presence. Where cameras see darkness, the instruments hear structure. Where empty space was once a phrase, a measurable singing medium takes its place. And in that song the far craft carry a truth that invites more wonder. Even beyond the sun's last breath, the universe hums and the hum can be read. He arrives at the line that is not a line, the heliopause where the last breath of the sun yields to the first steady whisper of the interstellar medium. The approach is long braided by the restless heliosheath layered by corridors of ordered field and patches of turbulence, and punctuated by the slow arrival of shocks launched years earlier from the inner system. The signature that matters first is in particles. As Voyager 1 moves outward, the low-energy ions that belong to the sun's wind fade in fits and starts dropping in bursts that look like rehearsals before a final departure. At the same time, the counts of high-energy cosmic rays rise, not as a single leap, but as a stair of steps, each step hinting that the craft has threaded another fold in a complex membrane. Then comes a day when the solar particles fall to a near silence and do not return while the cosmic rays hold their higher plateau. The change is crisp in species, even though other measures remain understated. The magnetic field strength increases modestly, the direction rotates only a small angle, and the plasma wave instrument hears a tone that marks an electron density now consistent with the interstellar medium. It is as if he has crossed a shore, where the smell of the sea changes sharply, while the direction of the wind shifts only gently. That day is written in the ledger as the crossing of Voyager 1 in the year 2012. The teams hesitate a while before naming it because the magnetic direction had been expected to twist more dramatically, but the weight of the particle counts, and the densities settles the question. Years later, Voyager 2 repeats the approach on a different latitude. Its direct plasma instrument is alive, so the readings now include the speed and temperature on both sides of the boundary. Inside the sheath, the plasma is hot and moving slowly outward. Just beyond the heliopause, it is cooler and denser, and flows with a different rhythm, a grace note that strengthens the case that the craft has stepped into a new medium. The energetic particles behave as they did for its twin solar material. Dwindle's cosmic messengers rise with confidence. The magnetic direction again turns only modestly. The second crossing, recorded in the year 2018, confirms what the first suggested: the heliopause is sharp in particle identity and in density, but subtle in field direction, a contact that behaves like a skin rather than a rigid wall. He watches the crossing through many senses because no single instrument can own the moment. The plasma wave tones climb to frequencies that match the higher electron density expected outside. These tones also bear the arrivals of shocks from the sun, which now echo more cleanly through a denser medium. The magnetometer notes a steadier field with smaller wanderings, as if the outside fabric is less tangled on the scales that the instrument can read. The particle counters record a new normal, in which high-energy cosmic rays are more numerous, and their variability tied less to the sun's cycle and more to the larger, slower mood of the surrounding cloud. Radio tracking continues to show faint twinkling caused by irregularities along the line of sight, and those irregularities now speak of structures that are no longer entirely born within the heliosphere. Each measure points to the same conclusion, while adding a shade of difference to the portrait. He considers the modest magnetic rotation not as a disappointment, but as a clue. If the interstellar field has been draping over the heliosphere for great distances, it may have trained the inner lines into a near alignment across a broad region, so that the final step does not demand a dramatic turn. Corrugations in the boundary could also smear the rotation. A craft that crosses a set of folded sheets will see many local angles that average into a small overall turn. Magnetic reconnection might stitch inner and outer fields together into a patchwork where direction varies in small domains, but looks similar across the span of an instrument's memory. The heliopause then becomes less a simple interface, and more a woven joint where geometry is distributed in space and time. On both crossings, the rise in electron density stands as the cleanest metric. The values inferred from the tones match the expectations for the local interstellar medium, several times higher than in the heliosheath. Steps within those values reveal layered substructure, as if thin skins of still higher density lie just outside the main contact. At times, the tones show a gradual drift in baseline, a hint that the ambient density itself changes over months, either because the boundary breathes under external pressure, or because the craft moves through minor gradients in the cloud. Such drifts matter because pressure balance at the heliopause depends on both sides. A denser exterior pushes inward, a thinner exterior releases the press. The shape of the bubble and the ease with which particles of different energies can wander across the contact will then shift accordingly. He reads the crossings as waypoints rather than endings. After Voyager 1 steps into the interstellar medium, shocks from the sun still arrive years later and ring the local plasma. The rise and fall of cosmic rays adjust slightly in answer to those visitors. The boundary behind does not seal like a door. It remains a membrane through which information passes. The craft continues to sample a place where the sun's influence persists as a faint tide layered beneath the larger sea. Voyager 2, following at a different latitude, observes a similar pattern and adds the detail that temperatures outside can be cooler than inside by a notable factor, a point that strengthens the image of a boundary crossed from a warm, stirred sheath to a cooler, denser exterior. He keeps close the sequence of rehearsals that came before each final step. In the months leading up to the crossings, there were periods when solar particles fell sharply, and then returned as if the craft had slipped along a magnetic highway, connected to the outside, and then drifted back into lanes still caged by the heliosphere. Those episodes taught that connectivity is not uniform. The boundary is skirted by linked routes that can open and close on timescales of days and weeks. When a corridor opens, particles of certain energies can exchange more freely. When it closes, the trade tightens. The final crossing becomes the time when such corridors cease to cycle and remain open in a persistent way for a wide range of energies. In the larger cartography, the two crossings separated by years and latitudes bracket the nose of a bubble that is not symmetric. The distances of the crossings differ, and the thickness of the heliosheath inferred along each path is not the same. These differences imply a bubble pressed by an external flow and field, with a nose that is slightly warped and a flank that is not a mirror of its partner. The interstellar boundary. Explorers' maps of energetic neutral atoms with their bright ribbon, aligned with the draped field, agree that geometry matters. The Voyagers provide the local ground truth where the ribbon suggests pressure and connectivity from afar, the craft field density, and particle identity on the spot. He's careful not to end the story here. Beyond the heliopause, a new learning begins. The particle populations include ions that were once part of the heliosheath and became neutral by charge exchange, then sailed across the boundary and became ions again in the interstellar medium. These fresh ions carry the memory of the sun outward as a faint echo. The magnetic field's steadiness is punctuated by tiny ripples that may be traces of faraway events drifting through the local cloud. The plasma wave instrument continues to hear tones that chart the density and the arrival of visitors from within. The crossing is a step into a different grammar rather than a coda. He ends the passage with a quiet speculation born of the modest magnetic turns and the strong particle steps. The heliopause may be best imagined as a living contact thin in distance, yet rich in structure, where identity changes suddenly, but orientation changes gradually, where lanes of exchange open and close with slow tides, and where the sun's last breath does not stop but diffuses into a larger wind. In that view, the act of crossing becomes both a measurement and a promise. It tells that the instruments have entered a new medium, and that the unknown stretches ahead thicker in electrons, richer in cosmic rays, steadier in field, yet still tuned to the faint rhythm of a star that now shines behind a membrane instead of within a bubble. He lifts his gaze to a weather made of particles instead of clouds, a sky of cosmic rays that carry the signatures of distant engines and of the bubble that tries to tame them. Cosmic rays are charged fragments of atoms, mostly protons, with a sprinkling of heavier nuclei and a minority of electrons and positrons born in violent places where shocks and magnetic turbulence can fling particles to energies that no human accelerator can reach. They travel near the speed of light, winding along magnetic fields that thread the galaxy, and when they meet the sun's domain, they find a shield that is strong in youth and softer with distance. The shield is the heliosphere, a bubble of solar wind and magnetic field that modulates the incoming rain. Near the planets, this modulation is familiar in the way counts fall during periods when the sun's magnetic field is tangled and powerful, and rise during the quieter years. Farther out, the modulation becomes a long slope. The pioneers and the voyagers feel this slope as slow climbs in the rate of higher energy particles stepped by the passage of large compressions, and muted by the aftermath of solar eruptions that sweep outward as travelling walls. When a broad shock leaves the sun detectors near Earth, often record a sudden drop in cosmic rays, a decrease named for the way an observer first learned to see it. That drop is a local sign of a moving barrier. Years later, the voyagers feel the faded echo of the same event as a soft dip and recovery proof that even after journeying billions of kilometers, the sun's storms still sculpt the rain. Along the long arcs of the twins, the pattern is not identical. Latitude and time weave together so that the northern path and the southern path trace different moods of the same sky. During certain phases of the solar cycle, charged particles of one sign drift along preferred lanes that hug the heliospheric current sheet, the wavy surface where the sun's spiral field reverses, while particles of the opposite sign prefer polar shortcuts. These charge sign-dependent drifts leave a fingerprint in the counts that would be hard to interpret near the inner planets alone. At high latitudes and great distances, Voyager 1 reads a gradient that differs from the one Voyager 2 later finds at lower latitudes, and the contrast implies that the shield is not a simple sphere, but a layered, tilted umbrella, whose ribs are set by both the sun's field and the interstellar field that presses from outside. In this mixed weather, there is also a class of visitors that owe their presence to the border itself. Neutral atoms from the local interstellar cloud drift inward, become ions by losing electrons, and are then swept up by the solar wind. These pickup ions can be accelerated at the termination shock to energies higher than the thermal bath of the sheath, but lower than the main galactic population. Their name reflects their origin story, and their rise beyond the giants was one of the early promises for what the termination shock might do. The Voyagers indeed recorded these particles a population that swells near the shock and then evolves across the heliosheath. Their presence matters because they carry a share of pressure that helps shape the sheath, and because their energy range overlaps with the lowest steps of the true galactic rain, making the separation of populations into a careful craft. He returns to the crossings because beyond the heliopause the balance of voices changes. When Voyager 1 steps into the interstellar medium, the counts of high-energy particles reach a new normal that is closer to the spectrum measured by instruments outside the heliosphere's grip. The rise is not infinite. Even beyond the border, the local interstellar medium is not featureless, and the craft continues to see small variations that speak of turbulence and of drifting structures in the external field. But the baseline is higher, and the coupling to the Sun's current mood is weaker. Years later, Voyager 2 finds the same pattern, adding the detail that the increase is energy-dependent larger in some energy bands than in others, which fits the picture of a membrane that was more opaque to some rigidities and more transparent to others. Rigidity in this context is the momentum per unit charge, and it determines how a particle threads through a maze of fields. Particles with higher rigidity are less easily bent and so treat the heliosphere as a thin lens. Particles with lower rigidity are steered more strongly and so feel the full breadth of the shield. This simple rule explains why the climb in counts toward the edge is steeper at lower energies, and why the final step beyond the heliopause gives a larger gain in softer bands. It also explains why the step-like rises during the approach often differ between the twins because their latitudes and the timing of their passages place them into different geometries of the wavering current sheet and the draped exterior field. Anisotropy adds another layer of meaning. If the incoming rain were the same from every direction, the counters would record an even glow. Instead, the instruments sometimes see a preferred bearing a small excess, arriving from one side, and a small deficit from the other. In the heliosheath, these anisotropies can arise when magnetic field lines connect more easily to the outside along narrow lanes, the magnetic highways that other instruments inferred from vanishing solar particles. Beyond the heliopause, anisotropies can reflect local patches of turbulence or gradients in the large-scale field. The values are small, but they are persistent enough across days and weeks to claim reality, and through them, the craft draw a compass rose for the unseen wind. He lingers on the way, cosmic rays and dust echo one another. When a shock passes, the dust lanes shift and the cosmic ray counts step in tandem, sometimes leading, sometimes lagging. Both obey the same geometry-charged grains, and charged particles follow fields and feel compressions, while neutral grains and energetic neutrals slip more freely across. The agreement is quiet but persuasive. It says that the weather of the edge is consistent across its actors, and that the same drape and the same changing pressure carve channels for both. The narrative deepens with the question of missing pressure inside the sheath. If high-energy particles above the main detector ranges contribute more than expected, they could help resolve discrepancies in the balance sheets drawn from thermal ions and magnetic fields alone. The Voyagers cannot count the very highest energies, but they witness the behavior of intermediate bands as hints. If these bands are more abundant than a simple model would allow, then their uncounted cousins at even higher energies may be providing an unseen push. This line of thought is cautious, yet it remains attractive because it could explain why the heliosheath sometimes appears under-pressured without invoking exotic physics. He then steps back to a broader scale. galactic cosmic rays carry information from supernova remnants from shock fronts in stellar winds and from the tangled regions near compact objects. Their spectra and composition encode the sources and the journeys. By measuring the local interstellar spectrum just beyond the Sun's border, the Voyagers deliver a ground truth that lets modelers subtract the Sun's modulation from near-Earth observations. The result is a clearer estimate of what the galaxy offers before the heliosphere edits the script. That clarity matters for many reasons, from understanding how cosmic rays shape chemistry in cold clouds to estimating their role in the subtle ionization of atmospheres on distant worlds. It also matters for simple curiosity. The numbers tell how harsh or gentle the universe is in a normal neighborhood between arms of a spiral galaxy. The speculative turn is gentle but insistent. If the local interstellar medium is not uniform, then the cosmic ray baseline outside will drift as the Sun moves. Over thousands of years, the heliosphere may pass through patches that are denser or more strongly magnetized, and the shield will respond by tightening or loosening. The galactic rain at Earth would then show traces of those drifts, perhaps preserved in ancient isotopes made in air and ice. On shorter timescales, changes in the drape and corrugation of the heliopause could alter the ease with which certain energies leak inward, producing patterns that future long-lived detectors might read as slow beats, superimposed on the solar cycle's melody. Through all of this, the far craft keep counting. Each small rise, each narrow dip, each angular preference is another letter in a slow alphabet. The conclusion is not a closed book, but a clearer grammar. The heliosphere does not stop the galactic rain, it shapes it. The heliopause is not a sealed wall, it is a selective membrane. And beyond that membrane, the sky of particles is steadier, denser, and yet not entirely indifferent to the star within its bubble. The wonder lies in the steadiness of the instruments that can read such a faint weather, and in the discovery that space between the stars is not empty but filled with a rain that never ends. He follows the field itself, the invisible scaffold that gives shape to the border, and he finds walls and folds where no solid surface exists. Magnetic fields in space are lines of force traced by charged particles. They are not strings one can pluck, yet they guide motion as surely as rails guide a train. Near the Sun, those lines spiral outward in a grand curve set by rotation and carried by the wind. Far from the Sun, where the wind slows and the pressure of the interstellar medium grows, the external field begins to drape over the bubble like cloth over a lantern. Draping means alignment and tension. The interstellar field presses, slides and wraps, while the inner field yields, stretches, and sometimes resists with loops and knots. The Voyagers read this drapery in the magnetometer as a slow trend towards steadier directions, broken by sudden jitters, a pattern that suggests broad sheets of ordered field separated by tangled seams. In places, the field strength rises without a matching rise in thermal pressure, a sign that magnetic energy is piling up into a barrier. Such a barrier does not have hinges or bolts. It is a zone where the field lines are squeezed together, raising tension and reducing the wandering of directions. The craft pass through such zones as if skimming the flank of a wall. Particles respond low energy. Solar ions fall away more completely along these stretches, while higher energy cosmic rays show clearer gradients. The radio listening at the edge where plasma rings in density tones often finds that such ordered stretches coincide with layers of higher electron density, as though the draped field helps collect cooler plasma into thin skins. He calls these places magnetic walls, not because they stop all crossing, but because they sort and slow. A wall in this sense is a region where field lines are packed and parallel over large scales, where diffusion across the lines is reduced, and where drifting along the lines leads a traveller to unexpected distances before any sideways motion is allowed. The result is not a seal, but a detour. The heliosheath shows hints of these walls in advance of the heliopause, and beyond the contact in the local interstellar medium, the trend towards steadier field continues, as if a matching wall exists outside with its own imperfections and seams. Between walls lie folds, the corrugations of a membrane under uneven pressure. Folds grow when the sun's wind sends out broad compressions that reach the sheath and push on the boundary, and when the external medium adds its own slow variations. A fold is not a tear, it is a curvature that turns the local normal in alternating directions. A craft that threads a folded surface will meet the boundary several times in layered steps, a rise in electron density. Here a temporary drop in solar particles, there a turn in field direction that is sharp in a moment and subtle across days. The series of rehearsals noted before Voyager 1's final crossing, when solar particles fell to near silence and then returned, fits the behavior of such folds. The craft brushed lanes where field lines linked to the outside and then drifted back into more isolated pockets, following the ridges and troughs of a corrugated sheet. Magnetic reconnection pours energy into this scene and opens shortcuts. When oppositely directed fields press together, they can break and rejoin in new pairings, forming islands and jets that carry plasma and particles along ephemeral paths. In the heliosheath, this process may stitch inner lines to draped outer lines, creating temporary portals. The particle counters see its fingerprints as energy-dependent exchanges. Certain bands rise first, as if their rigidities let them thread the newborn corridors while others lag. The magnetometer senses brief rotations and surges in field strength that accompany the reweaving. Where reconnection clusters into chains of islands, the field can become patchy, with pockets of ordered direction nested in turbulence. A craft wandering through such an archipelago reads a mixture of calm and riot over days, a sequence that turns a simple border into a gallery of magnetic sculptures. Remote maps support the idea that geometry rules the frontier. The interstellar boundary explorer, with its portraits of energetic neutral atoms born by charge exchange, sees a narrow ribbon arcing across the sky brighter than its surroundings, and aligned with the direction of the interstellar field that the bubble is draping against. That alignment speaks of a global fold, a place where field lines and plasma flows conspire to raise pressure and to favor charge exchange. The ribbon moves with the solar cycle and with large shocks, which implies that the drape itself flexes, tightening during active years and loosening during quiet ones. The Voyagers provide ground truth along two latitudes where the ribbon suggests a ridge. The craft later finds steadier fields, sharper particle sorting and higher electron densities, each a local echo of the large pattern painted from afar. He looks more closely at the ledger of pressure because walls and folds must be paid for. Where the field strength climbs, magnetic pressure increases and must be balanced by drops in thermal pressure or by unseen contributions. In some intervals, the numbers do not close without adding a term for particles of energies higher than the main thermal bath, but lower than the true galactic rain, a population that can be energized at the termination shock or within the sheath. In others, the imbalance suggests that tension stored in the folded field is doing work guiding flow and holding structure without leaving an obvious number in particle counters. These imbalances are not errors. They are clues that the joint between star and cloud is a machine in motion rather than a static sum. The folds do more than sort particles, they steer the wind itself. Flow vectors measured outside the termination shock and within the sheath show sideward deflections and occasional backflows. A fold that pushes inward on one flank can send plasma sliding along the face of a wall, gathering into a current that flows toward the tail. Where a connection cuts and reseals jets can form that point into the interstellar medium carrying bits of the sun's influence outward, and others that point inward, feeding energy back toward the sheath. In such a network of walls, folds, and jets, transport is highly directional. Drift along field lines carries signals and particles quickly. Crossing those lines is slower and more dependent on turbulence and reconnection. This anisotropy explains why the magnetic direction can remain modestly rotated across the heliopause even as identity changes sharply. If field lines inside have already been trained to follow the same chords as those outside the final step, samples a continuation rather than a perpendicular. In that case, the heliopause is a contact in species but a continuity in orientation, and the true shifts reveal themselves more strongly in pressure and density than in angle. He extends the view to timescales longer than any mission by picturing the heliosphere drifting through the local cloud. If the interstellar field strengthens ahead, the draping will tighten and the walls will stiffen, compressing the nose of the bubble and opening the tail. If the field weakens, the walls will slacken and the folds will flatten. These slow changes would alter how much cosmic rain reaches the planets, and how easily dust and freshly born ions cross the joint, modulating the exchanges that knit star to cloud. On shorter timescales, a cluster of strong solar eruptions can stack compressions that steepen folds and spark bursts of reconnection, briefly turning the boundary into a more permeable lace. The Voyagers have already recorded echoes of such stacking in the form of repeated density tones and stepped particle rises that march outward for years. He keeps the language plain because the structures are grand. A magnetic wall is a crowded region of field lines that guides motion along itself. A fold is a corrugation in the boundary that tilts the local face inward or outward. Reconnection is the cutting and sewing of fields that makes shortcuts and jets. Together they turn a theoretical surface into a living margin with architecture. The beauty is that this architecture is carved by nothing more than pressure motion, and field the simplest building materials of space, and yet the result is a coastline as intricate as any shore of rock and water. The far craft with their patient magnetometers, their ears for plasma tones, their particle counters and their radio links, timed to fine fractions, have given the first-hand sketches of that coast. The sketches agree on the main forms and differ in the details as two painters standing miles apart would see the same mountain with different shadows. What remains uncertain is how fine the corrugations run, how often the walls break into doorways, and how much hidden pressure flows in energies that current instruments cannot count. Those are not flaws in the map. They are places marked here be more invitations for future travellers to trace the folds with greater patience and to feel the walls with new senses. Until then the picture stands. The sun's bubble is wrapped in a draped field. Its border is ribbed with walls and creased with folds, and through that rich geometry the exchanges of particles and energy are sorted, steered, delayed, or sped, turning the heliopause from a mere line into a landscape. He follows the simplest atom to a place where it becomes a storyteller. Hydrogen, a proton with an electron, is the most common element in the interstellar medium, and the quiet backbone of the solar system's edge. Outside the heliosphere it drifts as neutral gas, warm by space standards yet colder than the stirred plasma within the heliosheath. Neutral means free from magnetic rules. Such atoms ignore field lines and can cross borders that bind charged particles. They slip inward from the local cloud past the heliopause without a pause and enter the slowed solar wind where they encounter protons heated by long travel. In that meeting an exchange often occurs. The neutral atom loses its electron to a hot ion, becoming a slow proton, that the wind picks up while the former proton gains the electron and becomes a fast neutral that shoots away. This charge exchange, writes the Frontier's grammar, the newly born slow proton is a pickup ion, a guest that adds mass and heat to the solar wind and helps it slow on the road to the termination shock. The newly minted fast neutral leaves as an energetic messenger that can fly straight unaffected by fields and later reveal where it came from. Instruments near Earth and in orbit around it, including a camera on the Solar and Heliospheric Observatory that maps ultraviolet light from hydrogen, have long seen a faint glow of backscattered photons as sunlight strikes these neutrals and they re-emit at the Lyman alpha line. That glow brightens in a belt downwind of the sun, where gravity and the flow combine to make a focusing cone, and it dims upwind. Subtle shifts in that glow across years tell that the influx of neutrals waxes and wanes with the solar cycle, as radiation pressure sometimes balances gravity and sometimes loses to it. The interstellar boundary explorer adds a different view by counting energetic neutral atoms arriving from the frontier after charge exchange. By mapping their directions and energies, it sketches where pickup ions pile up and where pressure concentrates, painting a ribbon, aligned with the draped interstellar magnetic field. Together, these views say that cold hydrogen is not a passive background. It is an active agent that feeds heat to the wind drives emissions that can be photographed and generates messengers that carry maps on their speeds. The Voyagers, along with the pioneers before them, and New Horizons in the Kuiper Belt feel the consequences in quieter ways. The pickup ions that form from hydrogen crossing. The heliopause and the sheath contribute pressure that shapes the termination shock in the heliosheath. On Voyager 2, where a plasma instrument remains alive, the temperatures and speeds measured just inside the shock show a warmed flow that theory assigns in part to the pickup population. At the shock pickup, ions are preferentially energized, forming a bridge between the thermal bath and the lower rungs of the cosmic ray spectrum. The particle counters on both Voyagers record this bridge as a population distinct from the true galactic rain, and its presence helps to balance the books when magnetic pressure and thermal pressure alone seem insufficient. The same exchange that makes pickup ions also makes fast neutrals that fly back into the interstellar medium. Those swift atoms carry the memory of the heliosheath's heat outward, and when they later become ions again beyond the heliopause, they seed a population that bears the sun's fingerprint into the larger sea. In that sense, cold hydrogen writes warm secrets on both sides of the border inside by thickening and heating the wind outside by carrying away a trace of the sun as a new family of ions in the interstellar plasma. Chemistry follows the exchange. Hydrogen atoms can attach to carbon-rich grains and to icy surfaces on small bodies, building thin coatings of simple organics in the deep cold. Cosmic rays thread through those skins and drive slow reactions that darken the coatings and form more complex chains. When neutral atoms and grains cross the heliopause, the change in radiation field and in charge environment alters those reactions. Some coatings sputter away under hotter ions, some grow slower under a different mix of ultraviolet light, and some become laboratories where unhurried chemistry continues for millions of years. The Farcraft do not carry full chemical labs in the outer darkness, but their dust counters and their particle spectra hint at these processes. Impact rates shift when strong shocks pass and charge balance changes, and faint anisotropies in count rates point to preferred lanes where charged grains and neutrals move together under the blended influence of gravity, radiation pressure, and draped fields. The idea of a hydrogen wall emerges from this exchange. As neutral atoms approaching from the local cloud meet inflowing pickup ions at the boundary, and transfer charge a region of enhanced neutral density, can form just outside the heliopause, a crest raised by the traffic of exchange and by the slowing of atoms that have lost energy in repeated interactions. Observations of stellar Lyman alpha lines seen through the Sun's neighbourhood suggest such a crest in multiple directions, and the interstellar boundary explorers' maps agree that pressure and density gather along arcs set by the external field. The Voyagers too close to see the global wall directly feel its influence as higher densities inferred from plasma wave tones just past the contact, and as steadier magnetic fields that fit a draped exterior. If a hydrogen wall exists as a real thin region of slightly cooler, denser gas, then it helps explain why electron densities step upward after the crossing, and why the final twist of the magnetic direction need not be sharp. The field lines are already running along a guided path held in place by the combined pressure of neutrals and ions. He watches how hydrogen mediates the sun's cycles. During active years, the solar wind carries more shocks and more ultraviolet light. Radiation pressure on hydrogen rises, pushing inward, flowing atoms outward more strongly. The focusing cone downwind thins, the upwind influx weakens, and the rate of new pickup ions lowers. During quiet years, the opposite holds, atoms fall in more readily. The cone brightens, and pickup ions thicken the wind. These variations propagate outward, changing where the termination shock stands, and how the heliosheath balances pressure along its flanks. Years later, those imprints reach the Voyagers as shifts in particle distributions and as changes in the cadence of plasma tones. Hydrogen thus becomes a messenger that carries the sun's mood far beyond the planets, not only as radiation, but as a living flow of atoms that change the very medium through which shocks travel. He draws a speculative thread from cold hydrogen to the ease with which cosmic rays enter. If the hydrogen wall is thicker in some directions because the external field presses more strongly, or because the sun is moving into a slightly denser patch of the local cloud, then the electron density and the neutral density just outside the heliopause would rise. Higher density can damp certain waves and alter crossfield diffusion, possibly changing how rigidities are filtered. In such a case, the pattern of cosmic ray gradients observed during approach and just beyond the border would shift with softer energies, either finding easier passage along draped lanes or facing stiffer resistance across walls. The twin trajectories of the Voyagers hint at such directional differences, and long-term monitoring may reveal slow drifts that betray pockets within the cloud. He keeps the language simple because the pathways are intricate. Neutral hydrogen crosses the border, freely exchanges charge, becomes a pickup ion, heats the wind, helps shape the shock, and becomes a fast neutral that can be imaged from afar. Those neutrals seen as a sky-wide glow in ultraviolet, and as energetic neutral atoms at higher speeds allow maps to be drawn of pressure and flow where no eye can see. The same atom is both a passenger and a reporter, both a coolant outside and a heater inside, both a veil that dims and a lamp that reveals. In this duality lies the phrase warm secrets. The hidden structures of the boundary are told by the coldest actors, and the long patience of the instruments turns their whispers into measurements. He ends the passage with a thought that fits the larger story. The sun's bubble is not divided from the galaxy by hardness alone. It is knit to it by exchange. Every neutral atom that slides inward carries a piece of the cloud into the heliosphere. Every fast neutral born in the sheath carries a piece of the sun back out. The balance of these trades sets the tone for the heliopause tunes. The density just beyond shapes the termination shock and modulates the path of cosmic rays. Hydrogen. The simplest element turns out to be the most eloquent narrator of a complex border, speaking in backscattered light in pickup ion pressure, in energetic neutral maps, and in slow shifts that only long listening can reveal. He listens for waves that begin far away, and for pulses born near the sun, and he finds that both arrive at the border and leave marks that last for years. A solar eruption throws out a cloud and a shock that race outward through the inner planets and then keep going, weakening, but not vanishing. As that front swells and merges with others, it becomes a global merged interaction region, a long belt of compressed magnetic field and thickened plasma that wraps around the heliosphere like a loose scarf. Near Earth, such a passage can bring sudden decreases in the count of high-energy particles as the moving barrier sweeps by. Far from Earth, the same event arrives as a softened pressure eyes a long increase in magnetic strength, a climb in temperature, and a shift in the speed of the wind. The Voyagers and other outward-bound probes record these arrivals as steps rather than spikes, a reminder that distance stretches everything into slower motion. The important part is that these fronts do not stop at the termination shock. They enter the heliosheath and keep their identity changing as they cross a medium that is warmer, denser, and more turbulent than the inner wind. The fronts steepen some gradients and flatten others, and as they approach the heliopause they push on the boundary itself. The interstellar boundary explorer sees the result from afar as changes in the brightness and shape of the narrow ribbon of energetic neutral atoms that arcs across the sky. That ribbon brightens or shifts when pressure increases along draped magnetic lines, and it dims or softens when the press relaxes, implying that the sheath and the local interstellar medium answers together when a train of shocks arrives from within. Voyager 1, already beyond the heliopause, confirms the story with a different sense. Years after a strong solar eruption, its plasma wave instrument hears a ringing at higher frequencies, a sign that the local electron density has been temporarily compressed. These tones arrive in sequences that match earlier activity near the Sun, and the timing aligns with when radio tracking and inner system monitors expected the fronts to arrive at that radius. The craft thus hears the Sun's heartbeat through a new medium, a tremor that proves that information crosses the boundary, even when particles of solar origin do not. He then extends the listening to ripples that do not begin at the Sun. The local interstellar medium drifts past the heliosphere with its own magnetic field and pressure variations. Faraway stellar explosions send shock waves into the galaxy that weaken with distance, but can still nudge the local cloud. Even the motion of the cloud through larger structures such as the edges of ancient superbubbles carved by many supernovas can impose slow gradients in density and field. These external changes push on the heliopause from the outside while the Sun pushes from within. The border answers like a drumhead that is struck on both faces, sometimes in rhythm, sometimes out of phase. When the external pressure rises slightly over months or years, the electron density just beyond the boundary can thicken, the draped field can stiffen into a more ordered wall, and the ease with which certain particle energies cross can change. When the pressure falls, the opposite occurs. The Voyagers cannot see the distant sources directly, but they register the consequences as slow drifts in their local baselines, a gentle trend in magnetic strength, a shift in the average tone of plasma waves, and a modest adjustment in the steady counts of high-energy particles that are not tied to any recent solar event. These slow movements hint at tides raised by distant suns rather than by the nearby star. The path of a shock is long, and along that path the character of the wave transforms. In the inner wind, the front can be sharp with a clear upstream and downstream. In the heliosheath, the front broadens and becomes a region of enhanced turbulence, where magnetic reconnection and wave-particle interactions eat away at sharpness and convert directed energy into heat and smaller-scale motion. That same turbulence can open and close corridors for particle drift, so that as the front passes, certain energies find quick paths along field lines, while others are momentarily caged. The particle counters reveal this by showing energy-dependent steps that do not line up perfectly, as if a gate opens wide for one band and only partly for another. When the front reaches the heliopause, it can push the boundary inward by a little and excite ripples that travel along the contact. A spacecraft near the threshold may then see a rehearsed sequence of changes: a brief fall in solar particles, a temporary rise in electron density tones, a tightening of magnetic direction, and then a relaxation as the ripple moves on. If the membrane is corrugated already, the passing front can shift, which folds are favoured and thereby rearrange the magnetic highways that provide easier connection to the outside. The rehearsals observed by Voyager 1 before its final crossing fit, this language repeated dips in solar particles that recovered, each associated with a change in field, steadiness, and with the arrival of a faded inner shock, as if the craft skimmed along ridges realigned by the press of a distant wave. He considers how the Sun's own long cycle composes the background on which these events ride. Over roughly 11 years, the magnetic polarity reverses and the pace of eruptions waxes and wanes. The heliospheric current sheet becomes more wavy during active years and flatter during quiet ones. This shape change alters the large-scale lanes along which charged particles drift. It also changes the azimuthal structure of the wind so that the merged interaction regions that later shape the sheath are launched with different angles and strengths. The result is a modulation of the border that is not only in pressure but in geometry. During active years, the heliopause may be more corrugated and more often agitated by arriving fronts. During quiet years, it may be smoother and less frequently perturbed, and the draped field beyond may relax toward a more uniform orientation. The Voyagers record this in the way magnetic fluctuations tighten or loosen over spans of months, and in how often the plasma wave instrument hears strong tones. New Horizons, far inside the sheath but beyond the giant planets, adds the echo by seeing the dust counter's rate shift, in tandem with the arrival of long faded fronts, a small proof that charged grains obey the same orchestration. He lets a cautious speculation unfold. If an ancient supernova shock much weakened drifts through the local cloud, it might raise magnetic tension and density slightly for a time long compared with a solar cycle. The heliopause would feel a firmer hand from the outside. The nose could shorten, the tail might stretch, and the cosmic ray baseline just beyond could shift. The interstellar boundary explorer ribbon might brighten or move a little. If after many decades that external press relaxed, the opposite changes would appear. The Voyagers with their long baselines could then catch slow trends atop the solar cycle's faster song. Already hints of such slow drifts appear as changes in the average electron density beyond the border, and as gentle shifts in the steadiness of field direction that do not match recent inner system activity. He returns to the simple theme because the physics is rich but the message is clear. The border is not a static shell, it is a responsive membrane. Shocks and compressions from the sun travel outward for years, arrive as travelling walls that thicken the sheath, ring the plasma beyond, and temporarily rearrange the ease with which particles exchange. Slow tides from the larger galaxy nudge from the outside, bending draped fields and adjusting densities in ways that the patient instruments can register. The two sets of forces add and subtract in combinations that turn the approach to, and the passage through the heliopause, into a record not just of where the sun ends, but of what the surrounding space is doing. The beauty is that one does not need a picture to see this. A timing of tones, a series of small turns in a magnetic needle, a handful of steps in particle counts, and a distant map drawn in energetic neutrals together trace the ripples. He ends the passage with a quiet image that feels earned. The heliosphere is a drum stretched across a frame of field and pressure. The sun taps it from within with bursts and cycles. Distant suns and ancient shocks tap it from without, and the far craft, steady and small, sit on the skin and listen for the tremors that tell how both sides keep time. He steps back to see the whole bubble and finds that its outline refuses a single sketch. The heliosphere is a wind-blown vessel travelling through the local interstellar cloud at about 25 kilometers per second, pressed by an external magnetic field that leans at a particular angle, and by a gas whose density is thin yet persistent. Inside, the solar wind expands until it meets that press. Outside, the interstellar medium drapes around the bubble and guides how the border folds. Early pictures imagined a classic comet shape with a round nose and a long tapering tail, but the record that the far craft and the remote maps have drawn makes that picture only a first draft. The crossings by the twin Voyagers occur at different distances and at different latitudes, with Voyager 1 stepping into the interstellar medium at around 120 astronomical units, and Voyager 2 at a somewhat shorter range, a mismatch that hints at a nose that is tilted and at a sheath that is thicker on one flank than the other. The difference is not explained by timing alone, because the solar cycle modulates the pressure from within, but cannot easily produce a lasting asymmetry by itself. The more persuasive writer is the interstellar field outside. Its orientation favours draping that is stronger in some directions and weaker in others, and that drape pulls the bubble into a lopsided form. Maps made from energetic neutral atoms born when hot ions exchange charge with cold atoms at the border, and then fly straight paint a narrow ribbon aligned with the external field, and show bright arcs that shift with the sun's activity. Those arcs imply ridges of pressure and connectivity that sculpt the global surface. Where the draped field lines gather into a magnetic wall, the border stiffens and the sheath narrows. Where they relax, the sheath spreads and the nose pushes outward. The Voyagers supply local truth to that distant portrait through steadier magnetic directions and higher electron densities in the same longitudes, where the ribbon suggests a ridge. The shape is not only asymmetric, it is time-changing. Over the roughly 11-year solar cycle, the sun's magnetic polarity flips the pace of eruptions, waxes and wanes, and long belts of compressed wind march outward. These changes collect in the heliosheath as thickened lanes that push on the heliopause months or years later. During active years, the nose can shorten by a little, the flanks wrinkle into sharper folds, and the tail can become more structured by streams that flow along magnetic corridors. During quieter years, the border relaxes, the folds soften, and the nose extends. The far craft witness this as slow, drifts in density and magnetic steadiness, as the arrival rate of strong plasma tones rises and falls, and as the gradient of cosmic rays shifts gently in response to the moving geometry. Even with this cycle, a deeper asymmetry persists that follows the outside field rather than the sun's mood. Modelling that treats the bubble as a magnetized plasma pressed by another magnetized plasma finds that the tail can split into two lobes under certain combinations of pressure and field, a croissant rather than a single taper, with jets of flow that wrap around the flanks. Flow measurements in the heliosheath show sideways deflections consistent with such wrapping, and the remote maps of energetic neutral atoms show structure downwind that refuses a simple single tail. The true tail is likely wide-structured and time-dependent, with regions of enhanced charge exchange that brighten and fade as fronts from the sun pass and as the external field evolves. Hidden pressure sources complicate the global balance. Pickup ions created from neutral hydrogen, that drift inward across the border, add heat and mass to the solar wind, and then are further energized at the termination shock, contributing a pressure that can be comparable to or greater than the thermal bath of the core plasma. Particles at energies above the main thermal population, but below the classic galactic rain, carry momentum that instruments count only partially, and their share must be inferred when the books do not close cleanly. Add to these the tension stored in folded magnetic fields, and the momentum carried by waves, and the result is a bubble supported by a mix of currencies whose exchange rates vary with time and direction. Where unseen pressure is higher, the heliosheath resists compression, and the heliopause bows less. Where it is lower, the border yields. This patchwork support helps to explain why the two Voyagers saw similar sequences of changes at the edge, but at different ranges and with distinct local accents. The bubble also responds to the composition and drift of the local cloud. If the sun enters a slightly denser pocket, or one where the external magnetic field becomes stronger by even a small fraction, the press increases, and the nose can draw inward over decades, altering how cosmic rays of different rigidities thread the membrane. If the cloud thins or the field slackens, the opposite occurs. Observations of backscattered ultraviolet light from interstellar hydrogen indicate a downwind focusing cone, and an upwind depletion that both vary with the solar cycle, and with long-term drifts a sign that the supply of neutrals that feed pickup ions and energetic neutral atoms is itself a time-varying actor. Because neutrals cross the heliopause freely, and then exchange charge, their changing influx modulates the pressure budget from the inside and from the outside at once, and therefore modulates the shape. In this way, even the simplest atom becomes a lever that moves the bubble's outline. The upshot is that there is no single distance to the border, and no single angle for the field at the crossing. Instead, there is a map whose contours shift by small but real amounts every year, a nose that nods with the sun's breathing, and with the slow tides of the cloud flanks that bunch into ridges when long trains of compressions arrive, and a tail that may divide and rejoin like braided river channels. This living outline explains several puzzles that once felt contradictory, a sharp change in particle identity at a place where the magnetic direction rotates only modestly, localized episodes of vanishing solar particles before a final crossing, differences in heliosheath thickness between northern and southern paths, and small, steady drifts in electron density well outside the heliopause. Each becomes natural if the bubble is lopsided, corrugated, and slowly changing with certain longitudes favoured by the draped field, and certain latitudes affected by the presence or absence of persistent folds. The speculation reaches forward to future travellers. A craft sent along a different longitude or at a different time in the solar cycle would find a boundary at another distance, with a magnetic highway either open or closed, with a hydrogen wall slightly thicker or thinner, and with the interstellar density just beyond a little higher or lower. Over centuries, as the sun moves through the local cloud, those differences would add up to a shifting climate of cosmic rays and energetic neutrals inside the planet's realm. Even now, the long patience of the deep space network which links Earth to these distant witnesses reveals that the shape of the bubble is itself a measurement of the neighbourhood, a three-dimensional barometer that reads the balance between a star's breadth and a galaxy's faint pressure. He ends the wide view without closing it. The bubble's outline is not a border drawn by decree. It is a consequence written in wind and field, and in the soft arithmetic of exchange. It bends where draping is strong billows, where hidden pressure rises and breathes with cycles launched under a distant light. What the far satellites have discovered is not only where the sun ends, but how that ending changes, and in that change lies the promise that the next crossing by another craft on another day will write a slightly different number and teach a slightly different curve. He stands with the far craft as their warmth ebbs and their messages thin, and he finds that fading light can still enlarge the night. Radioisotope thermoelectric generators that once ran comfortably hot now cool with the natural decay of their fuel. Each year yields a little less power, and each little loss demands a choice. Teams at the Jet Propulsion Laboratory move switches that once seemed permanent, turning off heaters that protected valves, sleeping instruments that had spoken for decades, reversing cables to share a stubborn watt between guardians that refuse to quit. The Deep Space Network leans in with larger dishes, combines antennas, polishes timing, and listens on the edge of noise for a carrier that quivers like a wire in winter wind. The signals arrive worn but not broken, and within their narrow bandwidths the story continues one slow line at a time. A magnetometer still turns field into numbers. A plasma wave instrument still hears tones that say how crowded the electrons are. Particle counters still add grains of knowledge to the grand tally of the sky's invisible rain. Even star trackers, now mostly idle, can be woken to help the craft find a calm attitude when sunlight no longer pushes enough to keep them steady. The art of endurance becomes part of the science. When a heater is shut off and a valve grows cold, vapor within might condense into a blockage. The teams weigh the risks because a colder valve frees power for an instrument that can still add a page to the book. When a memory bank is full and cannot be cleared in time for a new observation, the cadence is trimmed to fit what remains. In such careful rationing, the missions keep their shape, trading abundance for focus. The returns change in kind along with the power. Where once there were full spectra read at frequent intervals, now there are sparser samples chosen for the moments when passing shocks ring the medium, or when the baseline appears to drift in a way that promises a new contour of the interstellar sea. The Deep Space Network's clocks anchor every sample to an exact time, so that even thin sequences can be aligned with events at the Sun, and with the shifting ribbon seen by the distant energetic neutral atom maps. This alignment allows the final years to punch above their weight. A single burst heard far beyond the border can confirm that a shock has crossed the heliopause and that the local electron density has changed by a small but telling amount. Such moments stitch the waning local record to the broader tapestry that inner missions and Earth-based observatories continue to weave. Fading power clarifies questions rather than ending them. The gentle rotation of the magnetic field beyond the heliopause remains modest, even as the density steps are strong. Why should orientation change slowly when identity changes quickly? The ledger of pressure in the heliosheath still looks short unless an unseen term is entered for particles that sit between the thermal bath and the main galactic rain. Where do those particles gather, and how do they ebb as the sun cycle fades outward? The hydrogen wall that maps suggest beyond the border likely thickens and thins with outside pressure. How does that wall steer exchanges for different energies? And do its slow pulses appear as subtle drifts in the far counts? The two trajectories, northern and southern, remain an unfinished rhyme that begs for a third line at another latitude and another time. From these unanswered lines, imagination walks forward to future craft. He pictures an interstellar probe that leaves the plane of planets on a path that aims for the upwind face of the bubble, a design studied by the Johns Hopkins Applied Physics Laboratory, and partners not to retrace the twins, but to sample fresh longitudes with modern clarity. It carries a magnetometer of higher fidelity to read the draped field's geometry, without ambiguity, a plasma wave instrument with broader range to count densities without waiting for strong shocks. Particle telescopes tuned for the missing energy bands that likely hold the hidden pressure, a dust analyzer that can weigh and age grains to trace exchanges across the border, and a camera for energetic neutral atoms capable of drawing sharper maps of the ribbon from a vantage where Earth's glare and inner emissions no longer confuse the picture. It also carries radio beacons precise enough to let the deep space network and new arrays read faint scintillations along the line of sight as a continuous weather report. Such a mission could leave during a quiet solar phase to see the border relaxed, and then watch it gather wrinkles as activity rises. It could cross at a place where folds differ, measure the full rotation of field with instruments that keep their calibration to the edge, and then keep going for many decades until the chorus of local influences fades and the pure tone of the wider cloud stands alone. The speculation extends just a little farther toward instruments that learn to live on budgeted power, thermally efficient magnetometers that sip rather than drink, plasma listeners that toggle their ears open only when subtle precursors suggest a passing wave, autonomous schedules that shift cadence when the sun erupts, or when inner monitors report a stack of compressions marching outward. Even a new kind of power source may appear, a sail that steals a small push from the distant light, or a device that uses the tiny temperature differences within the craft to glean habitual trickles. None of these are promises. They're options born of what the fading missions teach about how a science of patience must be built. As the current craft dim, the meaning of their data brightens in other rooms. Modelers on Earth test global simulations of the heliosphere against the slow crescendos and silences recorded at the edge. When a model produces a hydrogen wall of the right thickness, a ribbon aligned in the right way, and a set of pressure balances that close without hidden terms, confidence in the unseen flows grows, and predictions for the tail become firmer. When a model fails to produce the modest rotations of field at the crossings, or the layered density steps beyond it is revised. The twins become both yardsticks and riddles, and in the act of resolving one riddle, subtler ones emerge. He takes care to keep the tone plain because the scene invites grandeur. A star breathes into a galaxy. The breath makes a bubble. At the bubble's skin fields drape particles, swap charge, and dust finds lanes that do not fit simple pictures. The twins cross and report that the membrane is a living joint rather than a wall. New horizons moving more slowly within adds the quiet economy of dust and the dimness of the background between galaxies. The interstellar boundary explorer staring from near Earth draws a sky-wide ribbon that responds to both inner storms and outer tides. Together, these lines reveal a border that will never be a single number. The message is now thin, but their echoes deepen because they belong to a long time and a vast place. He ends the chapter with a sense that questions are growing more beautiful as answers sharpen. How thick is the corrugation of the heliopause in the directions not yet sampled? How do draped fields fold when the local cloud changes on timescales longer than careers? How much of the missing pressure belongs to bands we have not yet learned to count? What shape does the tail take beyond the reach of current imaging? Each question is an impetus rather than a wall, and the fading voices of the far craft do not close the book. They mark the page for the next explorers to open with steadier hands, clearer ears, and the same calm appetite for mystery that sent the first machines into the long dark.